Okay, let's try now. Hello, hello. Yet again. Okay. Yeah, I have to switch my audio device every time between teaching on campus from my laptop to teaching from here. I actually use the little fish cam webcam as my mic because that's apparently the best quality and it's relatively close to my face. Um, so it seems to work fine so long as I tell my program that that's the mic that I want to use. Okay, well, I was just saying that I apologize for being a couple minutes late and asking how you guys were doing and commenting that it's nice for you because I'm the only one that can be late. You guys can show up whenever you want. Now, I do appreciate all of you guys for being here and saying hello and participating. So thank you for those that do watch live. I really actually do appreciate that a lot. Anyhow, here we go. So last time we talked about wastewater in general. Um, Updates on the exam grading. Yes, I have not touched them. I am just trying to stay above water right now with all sorts of things. I've got a one of my graduate students is defending his dissertation soon. Been trying to help him take care of that. Have my other class, been doing grading for that one. I hope to soon, but I've got my in-laws coming this weekend for Easter, and I can't spend much time working and don't plan to spend much time working over this next weekend. So I've just got a lot. I will aim to be grading them next week, and then maybe we'll go over the solutions to the exam. I think I'll hold off on going through those solutions until I have them graded for you this time, just since we're already jumping into the new topic. So probably won't have them finished for you next week. I will aim for the week after that. Yeah, no problem. Thank you for checking, and thanks for the understanding. That's just my current situation. So, but I will obviously do it, and I will do it before you are really studying for your finals. Okay, so that's where we're at. Next week I will begin grading them and your third homework. Okay, today we're going to talk about secondary treatment. So in our big picture wastewater treatment plant, we had some sort of primary treatment that usually consisted of a clarifier after some separation process like a bar and screen rack, then into the clarifier, and you settle out what you can. But there's still a whole bunch of junk in the water. And so when we go from that primary treatment, we would say that the effluent from the primary treatment, effluent is the fancy term for what's being discharged from a system. We'll say that the primary effluent is the secondary influent. So this primary effluent here, we could call it an influent to this next process. And then we have secondary effluent here. So this is just talking about the water portion. We technically have solids, as we'll see, coming from both of these as kind of an exit point. But in terms of the water, the effluent is how we're referring to water that has been discharged. Okay, so there's the primary treatment, and today and next time we will be focusing primarily on secondary treatment. Oh, and by the way, I meant to make some sort of April Fool's joke, and then I did not. So if you did not complete the take-home exam yesterday, then too bad. No, I was hoping to do something a little more elaborate, and it just time got away from me. But happy April Fools. Don't be fooled. Okay. Anyhow, we'll be focusing on secondary treatment, which is really within this control boundary here that we see. It includes the aeration tank itself and a clarifier. Now, one thing that happens here, and we'll get into more details, but we actually recycle some of the solids that settle. We take some of those solids and some of them go out the waste activated sludge, the WAS line. That goes to a landfill or to biosolids. We will typically press out all of the water there, or as much as we can, and then send for processing either for biosolids or just straight to a landfill. So we'll take some of the solids out, but these solids are primarily microbial cells. Excuse me. So when we have all these microbial cells, what we want is actually to recycle a fair amount of them so that when the influent water is coming in, we want that influent water to be able to have plenty of microorganisms ready to go and ready to eat their food. Because if we had no recycle, we just have basically sewer water coming in, it's going to have some bacteria, but not at the concentrations that we need to have quick, rapid, fully ready and going bacteria, like a good sizable population that's already consuming waste. We want that population that is actively consuming waste to be present so that we don't have to deal with the issue of needing to give them time to grow and reproduce and multiply in order to do the treatment that we need. So that's why we recycle a fair amount of that sludge waste and send it back into the beginning. It's not actually about getting extra treatment or whatever. It's actually just about getting this activated sludge tank to be producing plenty of bacteria and for those bacteria to be present in high quantities. So most of the biological activity we're going to assume happens within this aeration tank. Now, we'll talk about this, but we'll usually assume that no biological activity is happening in the clarifier, in part because we're not actively bubbling air through it. So there's not plenty of oxygen there, but also it just doesn't spend as much time there. And so we can conceive of the system as a biological reactor and then a system that separates the solids. Those two combined are what represent our secondary effluent. And there's an alternative. If we wanted to, we can actually use, instead of a clarifier, it's possible to use a membrane. And those are called membrane bioreactors. That'll be kind of a special topics type of a thing that we'll talk about in a little while, probably in one of the extra lectures. By the way, the syllabus, I think I still need to update it. I noticed the other day that this week, the classes for this week, I had somehow just completely missed. And so they were not on the schedule. We might be a little ahead of things compared to what I'm used to because I was in the schedule list. I didn't have this week. It didn't exist. So I will fix that. If I have not already posted that, I'll post a revised syllabus for you. Okay, so with that, I want to talk about the basics of this secondary treatment and talk about really wastewater microbiology is kind of what we'll talk about for the most part today, so that we understand the dynamics here of how these bacteria are growing and how much we're going to produce, how much they're going to eat given the amount of bacteria we have. So some terminology: a waste activated sludge, or WAS. This is essentially the slurry, the semi-solid stuff, just the junk. If you look into a wastewater treatment plant in one of these, it'll just look like that sludge. It's like it's liquidy, but it's also just muddy looking consistency. It's just a slurry of microbes, the waste, and all of the bubbles that are used to aerate it. Typically, we'll just simply use air for aeration. You could inject oxygen directly, and that would give the microbes even a bit of a better boost, but it's typically expensive, more so than it's worth to actually get oxygen, pure oxygen. So in addition to this aeration, one thing that this is the adding all of these bubbles is going to do is it's going to mix the tank. So if we think about the bubbles coming up, as they come up, they're going to be doing lots of mixing. And so when we consider this waste activated sludge system, we want to think of it as a CSTR, because we have a big tank, got lots of bubbles coming through, and it's essentially mixing the system pretty well. Another term that we might use, or you might see used in this this type of a topic, is the strength of a wastewater. And what we are referring to when we talk about wastewater strength is really the amount of biodegradable stuff. And when I say the amount of biodegradable stuff, what I'm talking about is specifically the amount of oxygen that will be demanded when the stuff is biodegraded. That's the BOD. We're going to go deeper into BOD after we talk about wastewater in general, but essentially that comprises any substance that microbes will eat and thereby do respiration and demand oxygen from their environment in order to do all that. So the typical values for BOD in wastewater are between something like 60 to 500 milligrams of oxygen demand per liter. Keep in mind that oxygen at saturation is temperature dependent. The hotter the temperature, the less oxygen will dissolve, which is actually one reason why cold water tastes better, by the way. The oxygen saturation is typically between 8 to 10 milligrams per liter. So if you took 1 liter of water, let's say cold water from the refrigerator, it's got 10, maybe 15 milligrams per liter of oxygen, and then you dilute it by 50% of a weak wastewater. So let's say the weakest here, you'll have half water and half of this wastewater. That has 30 milligrams per liter of oxygen demand in it. That will mean that all of the dissolved oxygen in that water, let's say if you sealed it off, will be consumed. Yes, and let me try to clarify. So what the amount of oxygen demand is needed in relation to the biodegradation. This BOD term is a metric that 1 milligram BOD equals 1 milligram per liter of oxygen per liter, that is, that will be demanded by microbes eating stuff in the water. So it might be the case that, let's say, 3 milligrams per liter of sugar corresponds to 1 milligram per liter of BOD. Something like that. Don't bother with this relationship. We're not going to take this type of analysis, but I'm just using it as an example as to how it might work. Okay, so some amount of sugar, fats, proteins, junk, carbohydrates, lipids, whatever's in the wastewater corresponds to some amount of oxygen that bacteria will consume given the food that's available. So you can think of wastewater like a dessert buffet, and the microbes are just really happy to eat all of that dessert, right? They just want to eat everything. When they do, they need to process it by undergoing the biological process called respiration. That's what we do when we breathe in oxygen. Our bodies react to that oxygen with food sources, sugars and things, and turn it from oxygen and turn the sugars from hydrogen bonded sugars into CO2. So we get some sort of organic carbon plus oxygen. Our microbiology within our cells converts that into CO2, releasing energy for us, and then we exhale CO2. The microbes are doing the same thing, or a very similar process, and they're consuming the oxygen and releasing CO2. This is a problem if we put the wastewater out into the environment, because then it's going to consume all of the oxygen that's available, and it will continue doing so for a long time until enough air has made its way back into the water to account for it. So even if we dilute it with water that's pretty clean, we can still have scenarios where you deplete all of the oxygen because the microbes are just hungry, they see the food, they're eating the food, and when they do so, they pull the oxygen from the water. Does that make sense? Did that help answer your question? Great. And thanks for the question. I know this is a weird metric. It's an odd kind of a topic. So it'll be good to keep in mind, and we'll spend more attention on how we calculate it and how to even model it if we do discharge some downstream. How far does it take before the oxygen reaches some minimum amount? Some things like that we'll get into after we do the basics of wastewater treatment. Okay, so that's the wastewater strength, and usually we're just measuring it in terms of this oxygen demand. It's kind of an oversimplification in terms of what all is in the wastewater, but it is one of those conventional pollutants. If you remember from last time, we talked about the conventional pollutants being the ones that are most apparent and the biggest issues facing wastewater treatment in general. The biggest motivators to have a wastewater treatment plant, you've got the oils and the grease, you've got pH, and you've got BOD. I think there's another in there as well, the suspended solids. But this BOD is what would cause fish kills by starving them of oxygen. So it's very apparent when you get a condition, and it starts to smell really bad when you get oxygen depletion, because different types of biological processes start occurring to process the junk, and then you get hydrogen sulfide, which is the kind of the rotten egg smell, and all sorts of nasty smells from that type of situation. So in terms of discharging waste, we want to treat it. One of the primary things we want to treat is the BOD. So that's kind of what we define, how we define our wastewater strength. Another term that we're going to use is volatile suspended solids. So this is different from regular suspended solids because this is the portion that you can volatilize. So I mentioned suspended solids last time. A total suspended solids, TSS, is essentially just a filter. You filter the water and see what mass of solids has stuck to the filter by drying and weighing the filter first, doing some filtration, and then drying and weighing the filter again and seeing what mass of solids has been added onto the filter during that process. I'm trying to use some hand motions here, and pardon me a moment while I adjust so that I can actually have my hands. So for the volatile fraction, that means that the volatile suspended solids are going to be any solids that can volatilize and escape as a gas, basically burn or evaporate, right? If it's volatile, it's going to escape and it's going to become some gas form when you burn it. And so the method here is to take that total suspended solids, where you took the filter, you poured water through it, you then dried it and weighed it, so you have a dry sample, some dry dirt, grime, junk, whatever, on top of the filter. Then you heat it at 500 degrees Celsius. So you basically take it and you put it in your oven and you turn the oven on clean, and maybe even goes hotter than that. So that temperature will drive off anything that can volatilize. Everything else that's left is going to be mineral in form of one form or another. It might be some silica sand grains that happen to be in solution. Maybe it's the ashes that are remaining from whatever biological mass was there. But this is going to be an estimate of the amount of bacteria in the water. And the reason it's going to work that way is because when we're doing this activated sludge, we're actually transforming most of the organics and stuff into bacterial mass, into bacterial cells. So this estimation then is going to give us the amount of mass that volatilized and went away, because essentially we weigh the filter, then we pass water through it and dry it and weigh the filter. That's our total suspended solids, that difference between the before and after the filtration. Then we're going to essentially burn it and then weigh it one more time in whatever is left there, the difference between the total suspended and this new measurement, that difference is going to be how much volatilized away. So that's going to be this volatile suspended solids, or VSS, measurement. And so this is giving us an estimate of the microbial concentration by mass. That's very handy because we don't know every type of microbe that's in there, and we don't need to. We want an estimate that we can use without concern as to what type of bacteria it is. We don't want to have to hand count them, looking through a microscope or growing them on some petri dish. That has problems itself because not all microbes grow on petri dishes. So this is just a really convenient, simple way to get an estimate of how much microbes we have. Okay, so thinking about what are the typical treatment outcomes we achieve, we have very often 95 to 98% of BOD removed. So if we think about, let's take the 95%. And then a low strength wastewater with 60 milligrams per liter of BOD, we can multiply that by 0.05. So we have just 5% of that remaining. So if we take, let's say, 5% of 100 is just 5. 5% of 50 then is 0.25. So this is probably something like, excuse me, 2.5 is what I meant. This is probably something like 2.7 or something, right? 2.7, not 0.27. And you could do the calculation for me if you wanted. It's somewhere around there, plus or minus some. Maybe it's 3. But essentially, that gave us a pretty good reduction, right? That's means that if we remove 95%, we only have a little bit remaining. But if we had 600, then we're still at something like 27 milligrams per liter of BOD. I guess I might as well be thorough about this and get the calculator out. Okay, it's exactly 3. So we'll say so you can see that the secondary treatment at 95% efficiency for low strength, that works just fine. That's probably reasonable. For high strength end, we're going to need more treatment because that's still going to take, even if you have a nice oxygen-rich stream that you're discharging to, you're still going to have a very significant potential to deplete all of the oxygen there. Okay, another way to think about treatment outcomes is in terms of the CNP ratio. This ratio, it's carbon, nitrogen, phosphorus. It's actually quite common in some fields, especially oceanography and some of the ecology and ecological microbiology, known as the Redfield ratio. So there are ratios that are known, for example, for algae, and that's where the Redfield ratio is referencing. We know exactly the typical nutrient ratio if we're to look at the amount of carbon versus nitrogen versus phosphorus in some living organism. You could look at the CNP ratio for human bodies, for trees, for snails, for algae, whatever it is. And so for the microbes, we have a typical ratio of something like 100 to 1 phosphorus, and then nitrogen typically varies between 5 and 20 to 1 for phosphorus, or 100 to that number for carbon. So what this means is you'll have 100 let's say this, 100 units or 100, let's say, grams of carbon for every 20 grams of nitrogen and every 1 gram of phosphorus per amount of bacteria. So that ratio, then, we can use it in a few different ways. One is just to simply understand something about the microbes. Another thing we can do, though, is to determine which nutrient is limiting. If we are supposedly going to grow more of these microbes, then we want to know, are they starving for phosphorus? In a lot of conditions and a lot of lakes and rivers and streams, phosphorus is the most limiting nutrient. And so in order to control unwanted growth, one thing you can do is limit one of these. Or if you wanted to spur on more growth, you would want to identify which one you need and add more of that. So an example of this was a tissue recycling plant I visited in Michigan, and this is actually common for almost all tissue recycling plants. Tissue, like tissue paper and cardboard and stuff like that, if you're recycling it to make something like a toilet paper product, what you want to do is you want to break down the fibrous materials and extract the molecular, on a kind of a molecular level. You want to extract those fibers and then use those fibers, get them to connect together, wrap them together, and then process them. You're going to use water for these different processing steps to get the fibers to stick together after stripping away all the junk and the stuff you don't need, and maybe bleaching it, doing some sort of chemical treatment. All of this is going to happen in water and then have separation stages. So you're going to end up with a lot of wastewater. That wastewater has a bunch of carbon in it from the various steps, maybe a little bit of fiber that didn't get caught up into the new product, and just the miscellaneous molecules that were in the cardboard they're going to contain a lot of carbon. And it turns out that a waste stream that's from the tissue plant is very starved for nutrients other than carbon. So this is high carbon, low N and P. And so in order to treat their wastewater, the microbes did not have enough nitrogen or phosphorus. There was lots of BOD in the water, and so they needed to remove the BOD, but that BOD was in the form of carbon. And in order to remove enough carbon, they actually had to add fertilizer. So they were literally taking gallon buckets or like jugs of chemical fertilizer that's normally used for plants, has some nitrogen and phosphorus in it, and pouring it into their biological reactor. And I think they had an automated system for this. But they would pour it into their bioreactor so that they could achieve a carbon, nitrogen, phosphorus ratio that was promoting microbe growth. Now, of course, they don't want to add extra because we also want to get rid of any excess nitrogen and phosphorus, but they would just add enough so that the microbes could be consuming it well. So there are implications here about limiting nutrients. We want to treat wastewater, yes, for BOD, and BOD typically relates with carbon for the most part. Nitrogen technically contributes a little bit as well, but a lot of times we just think about it in terms of carbon. So at some point, maybe you have excess nitrogen, but you're treating your carbon fine. In that case, maybe you want to add another process where you give the microbes a special condition, maybe an anaerobic condition where they can make use of the nitrogen compounds as an oxygen source, because nitrate and nitrite both have oxygens present that can be taken. So there are some special cases where we will design our wastewater treatment specifically to take care of these types of things, but generally those are what we would call tertiary treatment, not our secondary treatment. So we're going to put that kind of on the back burner for now, but this CMP ratio is important to understand when you have removal. Okay, so we have a link here. I forgot what this link is, so let me pull this link up and see what it is. One moment. So this is just a wastewater treatment plant. It looks like on the right here we've got probably sedimentation happening in a rectangular clarifier, and then on the left over here would be the activated sludge basin with all those bubbles coming out. So on the right, I think that would be either sedimentation, or maybe they're starting it off with the anaerobic process. No, that couldn't make any sense because it goes into air. So that's very likely a sedimentation basin right there. It's a rectangular one. Then they're taking that water and feeding it back through the channels into this activated sludge chamber, or probably the multiple ones. And then it's slowly moving through these chambers, providing lots of air as we see. And you can kind of see the sludge-like appearance of it all. So this person just kind of walking through. Skip through a little bit. It looks kind of like the water is moving pretty quickly, but I think that's mostly the effect of the bubbles making it kind of look that way. Of course, these are going to be designed with specific retention times involved. Now, one thing I'll note, if it was not already obvious, you really do not want to fall in there, which is why they have all these nice railings, because, obviously you don't want to fall into the wastewater treatment. I don't even need to say that, but you especially don't want to fall into it because all of these bubbles will mean that you have no buoyancy, which means you will sink and not be able to swim. So if you fell in there, you have to walk through it using, you're going to be partially buoyant, but not buoyant enough to swim because all the bubbles. You're going to have to walk to the nearest ladder, which are, in each of these there are ladders, because it's probably pretty deep too. And then climb your way out of the wastewater system. So it's actually quite a hazard that you might not think about. So yeah, don't fall into the wastewater treatment. That's actually also why if you're ever happen to be in a situation where you're on a boat and it's capsizing and sinking, you want to get as far away from that area as you can if you're swimming, because there's going to be lots and lots of bubbles coming up from it sinking. And if you're on a ship, likewise, you want to stay away from it, because you could potentially sink a vessel or yourself have difficulty swimming, given all those bubbles, creating a much less buoyant liquid where you're trying to float or swim. So that's kind of scary. So they continue walking through this, and I think over here we see, not sure what chambers these are. This could be some sort of might be disinfectant contactor chamber, although I don't think it would be that, given that it's open to the sunlight. And then their effluent coming out here. So perhaps that might be a clarifier that's mostly underground. But then you can see the water coming out. Still has a bit of color, but it certainly it will be higher quality than it was a moment ago. All right. And I think that's about it to just show kind of what it looks like from the other side there. So yeah, that's a good depiction of activated sludge there for you. And we'll come back to our PowerPoint. Okay, so moral of the story, don't fall into the activated sludge basin. Okay, so we want to know something about how to model, predict, understand the growth of microbes and how that relates to the amount of this waste substance we have. And I've got a sneeze coming, and I do apologize. Maybe I'll be able to mute myself in time. Maybe. Hang on. Okay. No sneeze yet, but might be coming. So in terms of the growth of microbes, we can use a term to understand the growth that is called the Monod equation. And this gives us a value for this parameter here, mu. And if you look at this value, this is a rate constant. So what we're looking at here is a growth rate that we're interested in, the growth of microbes, and that is the growth rate constant. So if we were to look at, and I'm going to use X for the microbe concentration as defined here. If we were to look at the dx dt, so how does the microbe concentration change with time, we can say that's going to be a first order growth equation which means we have mu as our k. Typically we'll have k, and in this case we have mu, and then we have x because it's a first order equation. Okay, sorry about that. So when we're taking a look at this growth equation, the simple form is dx dt equals mu x. And we see it's a growth equation. We've done a lot of decay equations, so make sure you're noticing here that this is going to be growth. That means if we have a CSTR and a growth equation, this is going to look differently than most of our previous work with decay equations. So we're defining this rate constant. We've defined different k values before, right? So we have mu this time. This is essentially our k. We've used lots of different k's. So in this case, we're defining mu, or the rate constant, in a particular way, just like we did when we were looking at flocculation, for example. We had an elaborate equation to solve for K. This time we have an equation to solve for mu that's going to depend on how much substrate we have. That's the BOD, or the food. So you see here that we've defined S as the substrate concentration in milligrams BOD per liter. That's how much food the microbes have to use. It's going to depend on that here and here. It's also going to depend on this mu max, the maximum specific growth rate coefficient. So this is like a rate constant, except this is the rate constant when the microbes have the absolute ideal conditions. They have as much food as they could ever possibly want, and they're not limited by anything. This is just the very fast they can possibly grow. So that maximum specific growth rate coefficient. So that times the amount of food divided by, and here's two parameters. One is the amount of food. The other is what we call a half velocity constant. This is essentially the amount of food where the microbes are halfway to their maximum happiness. So this is like this is the value of S. So KS here, this is uppercase K, by the way. There are a few Ks, and I apologize. I'm just sticking with the book's nomenclature. So the capital K with the subscript S is what we're talking about here. This capital KS, that's half velocity constant. This is the amount of food where the growth rate constant is equal to half of the maximum growth rate. So the microbes are basically halfway there, halfway to their ideal condition. So we can graph this to maybe make it a little easier to understand that. So we're going to say mu max, the very highest value of our growth rate constant. As we increase the amount of food, we're going to have some increasing amount of growth rate. So this is the growth rate constant. So this graph is going to look something like this, where we have some diminishing returns, and at some point we will reach that maximum, and it's going to look a little bit like an asymptote. And so what we'll do is we'll say, okay, well, at half, if we take a look at this graph and we say, well, halfway up the graph we have that half max. So this is 1/2 of mu max. Then we just simply see at what amount of food that corresponds to. So here, and then we draw our line downward and say, okay, well, this is our value for capital KS. So the half velocity constant is the amount of food where we have half of the fastest growth rate. So the growth rate is half as fast as it could be. And I didn't quite draw that scale, but you get the picture. So that's just what we know about KS. Usually we'll be given it. There are some common values, but I wanted to show you what it's referring to, so when you see this equation, it makes some sort of sense. So we then look at it and say, okay, well, the amount for, given some parameters, we can find the current or the appropriate growth rate constant for a given system, depending on how much food there is, and depending on how quickly the microbes can use that food given ideal conditions. And this parameter then shows us something about the shape, right? Maybe sometimes it would look like this, or like this. And so by providing that KS, we can know something about how long it takes before we reach that halfway mark. So it's a simple way to account for those types of changes. Okay, so let's take a look at what happens in reality when we put microbes in in a tank, give them air, give them water, give them food, and we stir and let them have a party, right? What's going to happen is we're going to grow more and more cells over time, right? If we look at how many cells there are, when we first put them in and first give them the food and everything, there is a bit of a lag phase before they start growing. They're just kind of acclimating to their new environment, detecting that there is food nearby, and then starting to activate, starting to consume, and then starting to reproduce. So for E. coli, for example, this takes maybe 2 or 3 hours. If you had some frozen E. coli and then put it in a nice warm area to grow, it'll take a couple hours before it really starts taking off. You can actually think about food safety in this manner too, right? If you have food and it's been kept in the refrigerator, presumably it's safe, and you don't have to worry too much about microbes growing. But let's say you make some sort of a, I don't know, potato salad or something, and you have maybe some, some eggs in it or something. Lots of nice nutrients. There's probably some bacteria if it hasn't been cooked all the way. Even if it has and maybe you've opened it before, there's probably some bacteria from somewhere. Well, a few hours outside of the refrigerator is probably not too bad because you're still in the log phase. But if you pass maybe the 2 or 3, 4 hour mark, especially if you've got some warm conditions, you're starting to activate them and you start growing bacteria like crazy. That's the case where you took your egg salad and you went on a picnic and it was a warm summer day, and then everybody at the picnic got sick who ate that because there were bacteria growing in that particular dish, because there were some great conditions and it was warm and it had been out for a few hours. So you'll actually see that in epidemiology. There are, whether it's a church picnic or gathering or something or some other event, there are outbreaks associated with exactly that scenario. So keep that in mind as you're dealing with your own food safety. If you leave something on the counter for an hour outside the fridge, it's probably no problem. Probably a good idea to make sure you don't do that too often to the same food item, but then be careful if you're getting past a couple hours. So you have this growth phase, starts accelerating, the microbes are growing, and eventually you're going to run out of real estate for the microbes. Either you just have too many, or there's starting to be not enough food. Usually it's kind of both. And so you basically have too many microbes and too little food to eat on, so they kind of start declining. You're no longer getting a net growth in the amount. You still have some growing, but at this point some are dying too, and the balance here gives us a stationary phase. So early on it's like they're almost all growing. Yeah, I guess some are dying, but given that it's there's plenty of nutrients and stuff, the growth phase is outweighing the death phase, or the growth is outweighing the death. During the stationary phase, they're equal. So this would be the growth rate, and this is like an equilibrium equation, right? Equals death rate. Then you have the death phase where the death rate is higher than the growth rate, and so then you've got bacteria dying. And if you were to do this in a 1 liter vessel, have it stirring, and it was something like E. coli and you gave it the right conditions, this might take something like 24 hours, and then it would stay there for another 24 hours or so, maybe 48, I don't know, just an estimate, just to give you kind of a concept of what this would look like. And then they would start dying off, and the viable cell count, so that means the amount of cells that can grow if you were to, let's say, put them on a petri dish, that amount starts decreasing at that point. So that's that's kind of what we can expect from the this the cells in terms of their growth rate. Now, one thing that will also happen as we are observing this dx dt, this whole graph is basically dx, right? How is that changing? Well, it's technically x, right? But what we're looking at is how it's changing over time versus time there. So if we compare that, we see that growing, at least for a time, and then at the same time, we'll have an inverse relationship with the amount of food because they're eating the food to grow. So if we were to map food on another axis here, the substrate would probably be declining kind of like this. Something like that that is a little bit of an inverse of the growth. So that mathematical balance is something that we're very interested in looking at and modeling. Okay, so how do we do that? Well, let's get the growth kinetics in play here. We have the Monod equation that we talked about, so that's our definition of the growth rate constant. The growth rate itself, as I mentioned, is going to be here, dx dt equals mu x. We can say that the rate of growth then, r sub g, is mu x, and we can substitute all of that stuff in for mu and say that our x times mu is x times mu max times s divided by ks plus s. Now, I want to highlight something here. This mu max and this ks, these can be known constants for a specific type of microbe, for a given microbe. So you could know something about your bacteria or your mixture of bacteria, about how they grow, and with that knowledge, then the only thing that this growth rate is going to depend on is how much food you're giving them, right? So that these two parameters here, with that knowledge, if you have that knowledge already, and you could probably do a pretty simple experiment to find it, then you can actually know how much growth you're going to get given how much food you give the bacteria. So that's very useful. Okay, so then we have a substrate utilization rate, and we're going to call this capital Y. We're going to define a yield coefficient that's going to help us understand our substrate utilization rate. So substrate utilization rate, this is going to be ds dt, right? And we need to know something about how the amount of microbes relates to the amount of food. So what mass of microbes do we get given some amount of food consumed? That's exactly this yield coefficient, milligrams VSS. And remember that VSS, that's the amount of microbes. So mass of microbes per mass of food is the yield coefficient. We have a lowercase k here, and we're going to define this. This is the maximum specific substrate utilization rate coefficient. Quite a mouthful here. The units are milligrams VSS, so the mass of microbes per mass of BOD per time. Okay, so this lowercase k, no subscript, is equal to mu max, so the fastest they can possibly grow, divided by that yield coefficient, how much mass of microbes we get per mass of substrate used or eaten. Remember, this k here is not the same as this k. So we have these two definitions here. This will make more sense once we get to kind of further along and look at our calculations. But just keep in your mind that there are different k's at play. They have different definitions and different associated equations. So this uppercase K does not really have an equation outside of its role within the Monod equation. This lowercase k, the maximum specific substrate utilization rate coefficient, that one has this definition here, and that's related to the yield coefficient. Okay, so with that, we can define our substrate utilization and our growth. We know the growth, we defined that already. Our substrate utilization rate then is actually just an inverse, so it's inversely proportional in some sense. I think I said that incorrectly. It's negatively proportional to the rate of growth. So as growth happens, substrate is removed, right? We know that growth requires the removal of substrate. So substrate will be negative when growth is positive, and growth will be positive. But it is also divided by this yield coefficient. This yield coefficient is giving us that milligrams VSS per milligrams BOD. So that's the conversion between this is BOD and this is VSS, and the Y here is VSS per BOD. Okay, so that's what allows us to make that relationship there. So it's actually pretty straightforward when we look at it that way. Yeah, that's right. Okay. Yeah, I think I'll just leave that there. That's probably useful. Okay, so that answers our growth rate and then how our substrate utilization occurs in light of the growth rate. Now the last portion of the equation would be the death and decay rate. So here we have, again, the graph that we were looking at, and we know there's growth, there's death, and there's, in consequence, there is also substrate utilization from here. So the death and decay rate we can define, so RD is defined as negative KD. So again, a third K here that the book has given us. This one is a lowercase with a subscript D. Okay, this is just a rate constant for the death rate. So keep in mind, there are now 3 different parameters that involve the letter K. 2 of them are lowercase with subscripts, and 1 of them is the uppercase. So KD is death and decay rate constant, again, per time units. And with that, it's pretty straightforward. We just need to know something about the death rate constant, and it's going to be first order in relationship to how much bacteria we have. So with all of that, then we want to define an overall net growth rate. And this net growth rate is going to be, we can call it R prime of G. So that net growth rate, that'll be the net change in X. So accounting for both the growth and the death. So the net growth is going to be equal to the growth plus the death. And of course, this term will be negative, and so those will balance. We can also define, remember, we can define the growth in terms of substrate utilization. So there's 2 things that can happen here. 2 ways we can use the relationship between growth and substrate. First, we can maybe predict how much substrate we will use given the amount of bacteria. But on the flip side, maybe we're observing the amount of substrate we use, and then we know something about how much growth we have. So depending on what we're looking at, there can be some useful tools involved here. So we have a net growth rate here, R prime G. We can define it, if we do that substitution, as negative Y times R of substrate utilization plus the negative KDX. Okay, so we're going to tie all of this together with an example. This is 6.9 on page 322. We're going to do a kind of a sequence of examples. First, we're going to start with a system where we have the biological reactor, but no clarifier. So we just have something coming in, something going out, and the biological reaction. Later, we will also include the recycle. So next lecture, we'll get into recycle and how that portion works. Right now, we're going to do just this reactor itself. Now, this is going to be a little more complicated than any of the problems we've done in the past in terms of the rate equations and the mass balances, because we are going to end up needing two different mass balances to work the problem. So example 6.9 here, and with an associated table of common parameters. It gives common parameters for K, for mu max, for Ks, for Y, and Kd in their units. We're also going to use default values. This problem mentions in the next step that it assume the default value. So we're going to use these values here. Okay, so in the problem, we have a shallow pond depicted here, and it stays well mixed due to the wind and the steady flow of a small creek. So we've got a creek flowing in, the pond, the creek flowing out. The total volume is 200 cubic meters, and essentially the problem is going to continue and ask on the next page what the final bacteria concentration is, XF, that is leaving the pond, and what is this final substrate concentration, SF, that's leaving the pond. So those are the two things that we're going to solve for. And essentially what you'll see, since this is a CSTR, it's well mixed, it's got an inflow and an outflow, we know that X equals XF and S equals SF, right? So that's just showing us what we need to solve for. Okay, so given that, start thinking to yourself, how would you go about solving this problem? We need to find the amount of substrate that's left over and the amount of bacteria that we've grown. So we'll end up using those equations we were just looking at, the growth and the death, and that substrate utilization in order to solve this problem. So if we were to look on the next page, it says the microbes in the pond consume the inflowing biodegradable organic matter according to typical kinetics. If that's the case, then determine A, the BOD leaving the pond. So this is going to be SF. B, the biodegradable organic matter removal efficiency of the pond. This is just going to be, what we started with minus what we ended with, divided by what we started with times 100%. Should be pretty simple once we got A. And C, the concentration of volatile suspended solids leaving the pond. So XF. So those are the three things we need to solve for here. And I'll go ahead and give you the start of the solution. It says the pond can be modeled as a steady state CSTR because it is well mixed. And we'll assume the stream flow has been at a steady flow rate and composition for a long period of time. So part A, it suggests that first you want to set up a mass balance on the microbial concentration, microbial mass, using the pond as a control volume. In the variables in figure 6.14, based on those things, we can write a mass balance as what's coming in, so 0, so steady state, equals Q x naught, what's coming in for the microbes, minus what's leaving, minus Qx final plus the growth, the net growth in that volume. Okay, it's a little bit counterintuitive here, but one thing you'll see, and this is why I'm starting you in this direction, is you'll see that in order to solve this problem, to find the substrate concentration, you actually need a mass balance on the microbes, because the microbes are what are consuming the substrate. And if you look on the previous section, we know how much microbe concentration is coming in. It's actually 0. We know how much substrate's coming in. And so given that, we have some amount of microbes that will be growing, and essentially this will go to 0. And then we're just left with how many microbes are leaving compared to how much are growing. And it will turn out that we can get the microbial mass or the microbe concentration value to cancel and be left just with an equation for S. In terms of the known parameters. And it's a little counterintuitive that way, but we can do that, and then we can do a mass balance on substrate for the other one to get an equation. Given that we now know the substrate leaving the pond, then we can solve for X in that case. And we have the known S. So it's a kind of an interesting situation. This really only applies to the case where we have no recycle. So there's no recycle of microbes, meaning the X naught is 0. So that's an important component of the mass balance and the way this is going to work when we solve it in the situation here. Okay, so we've only got a few minutes left. What I'm going to say is practice this on your own. Work towards coming up with a solution on your end. And then next time we get together next week, we'll begin here and we'll go over this problem. So I'll leave it at that for today. So if you've got any questions, let me know. And if not, have a good Easter. And in the meantime, I think my fish needs some food. Oh, thank you. So we'll go ahead and feed the fish. Give you a moment for any questions. The fish has become less camera shy during the course of the semester. All right, well, I will see you guys next week. Have a good weekend.